Calculating the pH of a buffer system. You can calculate the pH of a buffer solution in a variety of ways. You can treat it as a common ion problem and do a full equilibrium calculation with the Ka or Kb of the acid or base, or you can recall the Henderson-Hasselbalch equation and use it, because we can make some assumptions when we have a buffer solution. Further, you can calculate the pH of a solution. I don't even have to say that it's a buffer, because you can recognize this particular solution as a buffer solution because it is a solution, and in that solution it contains a 0.15 molar solution of a weak acid, HNO2, and a 0.2 molar solution of the salt, sodium nitrite. Now, this particular salt, of course, disassociates 100%, so I can think about this solution as having the weak acid and the conjugate base partner of the weak acid in a substantial amount, 0.15 and 0.2. Given that I have the acid and the conjugate base partner, I can go ahead and use the Henderson-Hasselbalch equation in the form for the pH. And the pH equals the pKa plus the log of the quotient of the weak. The pH equals the pKa plus the log of the quotient of the anion of the acid, and you can just abbreviate it A, divided by the weak acid. And in this case, we use the initial concentrations because the ionization is suppressed. It's so small that the X ionization is going to be able to be ignored. Okay, so first of all, we're looking for the pH. The pKa, we can either look it up in a table or we can calculate it based on the Ka. The Ka for the acid HNO2, nitrous acid, is 4.3 times 10 to the minus 4. So the pKa of that acid is just the negative log of the Ka, which is equal to 3.37. Okay, so the pH equals the pKa 3.37 plus the log of the initial concentration of the anion, or the conjugate base partner of the acid, which is the sodium nitrite, which is 0.2 molar, divided by the acid is 0.15 molar. Okay, and when you do the math, you end up with pH equals 3.37 plus 0.125, which equals 3.49. So the pH of this particular buffer system is 3.49.